Okay, so I'm just repeating this just for the recording. The sketching of the polynomials, you're going to, so sketching the polynomials, we're going to do the things that we did before. We'll consider the degree and the leading coefficient to give you the basic shape. Is it going to open up, down, x to the power of 4, x to the power of 3? The leading coefficient will tell you that. Factor and find the roots, so you can see all those x-intercepts, all those spots. So set each factor to 0 and figure out where it's going to, what it's going to do with the roots. Then you explore the order at each of those points. Is it going to cross, meaning the order is 1, so it just, the line goes through. Is it going to touch? So when it's x squared, remember it bounces off the root, either comes up like this or down like this, or x cubed is going to flatten. And then what's new is we're going to add the critical points. So not just before, when we sketched it yesterday, we figured out it goes up to here and down to here and come back, but we were guessing how high. Now we can do what we just did in our last lesson to figure out the exact critical points. Set the derivative equal to 0 and find the local maxes and mins using the chart. If there are points of inflection and concavity, this is where you would go off and find it, but we're not going to do that step right now, but it is helpful. You take the second derivative and set it equal to 0, but we're not going to do that step, but I am putting it in here just so you're aware of it. And then, of course, the last step is to sketch. That's for polynomial functions. When it's a rational function, polynomial functions don't have asymptotes, so when it's a rational function, you're going to find the vertical asymptotes. So that's our first step. And then last, in advanced functions, we did test points. But here we learned about limits, so we're going to formalize that a little bit more and take the limits on the left and right. Then you go off and do the horizontal asymptotes, which are either going to be at 0 or someplace other than 0. If it's at 0, you're going to just take the limit on the positive or negative infinity. And when it's not at 0, you might need the directrix, like we did yesterday in asymptotes. We're not going to do any oblique asymptotes in this video, but you could, oblique asymptotes could pop up at this stage. Then, of course, you're going to find the x and y intercepts, really critical or important spots. For polynomial functions, the x-intercepts of roots. Here, we might just have 1 or 2 x-intercepts for rational functions. And then here's the new part, adding the critical points. So again, if we have any bumps or any parts of the rational function that come down, we can be more specific and accurate by finding the critical points. If points of inflection and concavity, this is where we come up, and then you're going to sketch. So again, both of these procedures look the same at the beginning. What we're adding into it in this video is the critical points. All right. So let's now actually redo the question that we did the other day on taking up one that we would have done before, but just we're going to be a little bit more accurate. And we'll go through a little bit quicker. If you find I'm going too quick from the stuff we did yesterday, you can go back and watch that video. But I think we'll be able to get this. I just want to key in on the critical points that we're going to add on to this to make it a little bit more accurate. All right, so when we get going on this, we're given the function. This one is a polynomial. You know it's a polynomial because you're not dividing by anything. Everything's going to exist. So the first thing we're going to need to do is find the roots. Before we can find the roots, we must factor it. It's much easier to deal with these in factored forms. So in this case, we're going to take a common factor, and x squared is a great common factor. Divide x cubed by x squared, we get x. And divide 3x squared by x squared, we get 3 or minus 3. Again, you can always check to make sure you did that right by rainbowing back and make sure you get the question. All right, now we got to find the roots. The roots are going to come when this is equal to 0. So 1 root or 2 roots or something like that might come from this one. And another root's going to come from this one. You guys are probably experienced enough to be able to see that the first one is going to be a 0. The square root of 0 is 0. not plus or minus 0, you don't need that. You know that the root there is 0. And again, you probably won't write down this line, x minus 3 equals 0, because you're getting so good at seeing that the root from that factor is 3. So those are the roots. We know already those 2 points. So I'm going to plot those onto my graph here. Something's going to happen at 0, and something's going to happen at 3. What I want to know is, what's this graph going to do? The order of 2 is going to tell me that it's going to touch. So my graph is going to touch at that point. And then this one has an order of 1. It's just a plain old, this factor is x to the power of 1, so I know it's going to cross at this spot. So I know how it's going to behave at these 2 points. Now, I realized that I skipped ahead and did step 2 here, and I forgot step 1. Consider the degree and the leading coefficients. So to get the basic shape of it. So I forgot to do that part. Let's go and do that right now. So if you look at this, the degree is 3. And the leading coefficient is positive. So already in my mind and from all the experience in advanced functions, I know that this is a degree 3. So it's either going to go like this, opposite end behaviors. But this one is positive, so it's going to go up from the left to the right, up there. So it's going to start down here and end up here. At this point, we would be finished in advanced functions. And this is what we did in the review yesterday. And then you would do a sketch. Now, don't draw this, but this is what we're imagining in our head. It's something like that. But what we want to do now is figure out exactly where that spot is. So I'm not going to draw that. I'm just imagining that in my head. I'm now going to go on to the next step. Let's make sure I haven't forgotten anything else. So I did the degree, I factored, I explored the orders. Now I'm on step 4, find the critical points. This is the new part. So my original function is x cubed minus 3x squared. So I'm just writing it down so I don't have to keep looking up at the top of my screen. It's right there. I have to differentiate it. Obviously, the first step in the derivative rule is to take the derivative. So the derivative of 3x squared, the derivative of x cubed is 3x squared minus 6x. Again, since it's so important, you might just want to double check that you did that right. 3 comes down, 1 less is 2. 2 comes down, multiplied by 3 is 6. 1 less is 1. So I look good. So there is the derivative. And the first derivative test, I said equal to 0. What you see is I have a quadratic. That quadratic can be factored to solve for 0. In this case, an easy factoring is a common factor. I see a common factor, not just a 3, but an x. I see a 3 and an x in both of these. 3x squared divided by 3x is just x. And negative 6x squared divided by 3x is negative 2. So I took out a common factor of 3x. Again, I can always check, did I do that right? 3x times x is 3x squared. Yep. 3x times negative 2 is negative 6x. Yep. So it turns out that I'm going to end up with 2 critical points here. One of them is going to come from this being 0, or the other one's going to come from this being 0. Again, you guys probably won't write that down because you're so good at seeing the zeros. And you can see that this one is going to be a 0, and this 0 is going to be 2. So what you know now are exactly where these critical points are going to occur. One of them is going to happen at 0, and one of them is going to happen at 2. Now I need to find their actual point on the graph. So not just whether it happens at x, but where is the y value. So I'm going to take this and plug it into my original. So my original is right here, so that's handy. So where is the actual point? So when I plug in 0, it's 0 cubed minus 3 times 0 squared. 0 minus 0, 0. So therefore, one of my spots, oops. One of my spots is 0, 0. The other spot is going to be where x equals 2. So I put in 2 cubed minus 3 times 2 squared. 2 cubed is 8 minus 2 squared is 4 times 3 is 12. And so that's negative 4. So therefore, my other critical point is going to be at 2, negative 4. Okay, so set the derivative equal to 0. Found the two spots, the x values, found their corresponding coordinates. And now I've got two critical points. I can plot these on the graph right now. Okay, so I'm going to go here and plot these on as critical points. 0, 0. Okay, that's a critical point. That's good because I already knew about that guy. I also knew it was going to touch, so that's good. And then 2, negative 4. So 2, negative 4 is down here. There is another spot. So already I've got a great idea of what this picture is going to look like. And I'm going to be more accurate than my first attempt because I can see now that it goes down a lot lower than I suspected. Truthfully now, you have all the information. Well, that dot got a little bit away from me. Truthfully, you have all the information to do your sketch. But the math that's required here is to prove what those critical points are doing. Although we're pretty confident this first point is a max and the second point is a local min, this is where the chart must come in to prove it. Okay, so half of this question is sketching, half is proving that it's correct. So underneath here, I'm going to do the chart, just like what we just did in our last lesson. So we're going to investigate what the derivative does and what the actual graph does. Now we have two critical points. We've got 0 and 2. So again, you can imagine the number line. If you want to sort of draw this down here as rough, you know that you've got a spot at 0 and you've got a spot at 2. That means you've got to consider 3 chunks. Everything less than 0 is the first interval. So I'm going to go x is less than 0. 0 is the first spot. Next. What's happening in between the two critical points? So between 0 and less than x and less than 2. And then the last spot is at the end, everything bigger than 2. X is greater than 2. I'm going to stop here because I think the spot where people struggle the most are coming up with these interval parts. So if there's any questions, let me know here. I sort of did this one for you. The next one, I'll get someone to do the intervals for me. All right. Okay. Now, we're doing the chart and we're investigating to see what the derivative does in these intervals. So we have to take the derivative. So here's the derivative. But remember, we it's easier to do the derivative in factored form. So I'm not going to investigate the derivative there. I'm going to investigate it right here. Because I already put it in factored form. So I want to know what the derivative is going to do like that. Okay, so I'm going to use that version of the derivative instead of my first version because it's factored for me. So I'm always going to be looking at this when I plug in numbers in these intervals. Now, the 0 spot, I know the derivative is 0, and 2, the derivative is 0. Right? I already figured that part out from the critical values. So what I'm really interested in is what happens before the critical point when x is less than 0. So again, you imagine a number less than 0, pick something that's easy. I'm going to choose -1. When I put -1 into this part, 3 times -1 is going to be negative. And when I put -1 in this part, it subtract 2, I get further negative. So it's going to be a negative times a negative, which is going to be positive, which means my original graph must be going up. Zero, I know it's 0. Next, this middle section between 0 and 2. Pick a number that's easy. I think 1 is really easy. 3 times 1, positive. 1 minus 2, going to go negative. And notice any number in between there, even if you chose like 1.9, when you subtract 2, it's going to be negative. So anywhere in there is going to be negative. You might as well pick an easy one. So this will be a positive times a negative, which is going to be negative, which means the graph is going to go down. Then I'll look at the last step. The last step is a number bigger than 2. What happens there? So I'm going to choose something like 3. 3 times 3 is going to be positive. And 3 minus 2 is also going to be positive. I've got a positive, so the graph is going to go up. And so this chart really proves what I already imagined. The graph's going to go up, get to 0, go down in the middle section, get to 0, and go back up. And so if it's going up, up, getting to 0, and down, this is a local max. And then it's going to go down, get to 0, and go back up. So this is a local min. So again, we need this as the proof part of our work, but the actual drawing isn't changing. We just now know that this guy is a local max and this guy is a local min. And so we've got everything we need to get a little bit more accurate picture. And now we're going to draw it. We know it's a degree, it goes up, its leading coefficient, it's going to start here, it's going to bounce off here at the max, come back down to the min, and then go through that point and cross through that point. And so we get a much more accurate picture of our polynomial. Because this is more accurate, we're going to label the axes now. So this is 1, 2, 3. This is -1, -2, -3. And the critical points can also be labeled. So this critical point, remember, it's down here was 2, -4. There it is, 2, -4. And this critical point is 0, 0. And so we end up with that, all of that as the math to prove our sketch. So, lots to do, I know that. This is why I left this till the end, so that we'd have all of today, the weekend, and you can even have some time on Monday if you want to be able to do these, okay? All right, so this one is a polynomial. We should do a rational function one. So we're going to do another example here where we'll go through the whole step, all the steps. Now that we're going to have asymptotes, it's going to be even more steps to be able to draw another one. Any questions on this guy before I leave it? All right. Good job for a Friday morning. We're doing great. Okay, again, I've decided to pick one that we've already seen. We're just going to tidy it up a little bit. All right, so again, we've done some work on this, but yesterday when we did it, we did test points. And here we're going to use limits. So we'll tidy it up. So already we should recognize that this is a rational function as opposed to a polynomial because you have one thing being divided by another thing. We're going to end up with some asymptotes. So here is our algorithm for sketching rationals. We're going to do vertical asymptotes first, check their limits. Horizontal asymptotes, check their limits. If we need to get the directrix, we will. All right, so vertical asymptotes. Let's see if people are awake out there. Can someone tell me the vertical asymptote on this guy?
-2.
-2. Excellent, thank you. You can see it from where it equals 0. I doubt you'll write this, but there it is. Okay, x is -2. All right, now last year we would have done test points on this. We would have done -2.1 and -1.9. Same concept, but now we write the limit as x approaches -2 from the left. So this part is new. We'll make sure you write this part down. And we're going to do the limit as x approaches -2 from the right. In our head, what we'll do is do exactly what we did before. We're going to pick a number that's just to the left of -2 and plug it in and find out if it's going to be positive or negative. So I'm going to, in my head, think of -2.1, okay? But I'm not writing that down now. I'm using this notation. But -2.1 minus 3 is going to be negative, and -2.1 plus 2, not big enough to get out of the negatives, we're still at negative. And so this will be a negative times divided by a negative, which is going to be positive infinity. Similarly, in my head, I'm going to pick a number just to the right, which is -1.9. I'm not writing this down. I'm just in my head. And I'll do the same thing. -1.9 minus 3 is going to still be negative. Get further negative, actually. And -1.9 plus 2 now gets me to the positives. Okay, it's going to get me over that threshold to be positive, which means I have a negative on the top and a positive on the bottom, which is going to be negative infinity. So exactly the same concept of what we did before, but our notation is a little bit more formal in that we have these limits. But we've got our first bit of information on our sketch. So let's throw this bit of information on there. We'll grab our asymptote. We'll draw, oops. Hello, what's going on? There we go. We'll draw our asymptote at -2. And This tells me that from the left, it's going to positive infinity, and from the right, it is going to negative infinity. Okay. Next, horizontal asymptotes. The horizontal asymptotes, we compare the degree on the top with the degree on the bottom. This is x to the power of 1, so the degree on the top is 1. The bottom is x, degree in the bottom is 1. So n equals m. And if you think back to yesterday when we remind ourselves of oblique or horizontal asymptotes, when n and m were equal, we need to look at the leading coefficients. The leading coefficient of this guy is 1 and 1, and so the horizontal asymptote is going to be 1 over 1, which is y equals 1. So the horizontal asymptote is going to be at y equals 1. Let's draw that on our graph, and then we'll figure out what we need to prove with this horizontal asymptote. Now, last year, because it was at 1, we couldn't go any further. We couldn't plug it in to figure out if it's above or below, because above and below are both going to be positive. But what we learned yesterday is if we can't do it using this, we're going to use the directrix. So the directrix is found by taking the top number and dividing by the bottom number. So you see it's x minus 3 divided by x plus 2. So over here, I'm going to go x minus 3 divided by x plus 2. So what our step is then, we go through and we say, okay, what number do I multiply by x to get x? That's easy, that's just 1. So I write down 1 there. And then I do a little mini rainbow. 1 times x is x, 1 times 2 is 2. And now I have to subtract. Of course, the x's disappear. And be careful here, this is minus 3, subtract 2. Minus 3, subtract 2 gets me lower, and I'm at negative 5. The remainder is what's important here, because that is the top of our directrix, and the bottom is the same as what's on the bottom of our original. And so now we have this directrix. Just as a little curiosity here, the answer right here is actually the horizontal asymptote. And so you see how the answer is 1 and the asymptote is at 1. If the answer here was 2, this asymptote would be at 2. And if that answer was x plus 2 or something like that, it'd be an oblique asymptote, and that'd be the equation, the oblique asymptote. That's just an extra little curiosity to make sure that you're right. We don't need to identify that because we already know the horizontal asymptote is that. All right, the whole point of getting the directrix is so we can do our limit test on the directrix instead of on the original. So we're now going to do the limit as x approaches negative infinity of the directrix. Remember, we're talking horizontally, so we got to get a really big negative number, a really big negative number, and a really big positive number. That's the directrix. And we'll do the limit as x approaches positive infinity on the directrix. So we choose a number like negative 1 million. We plug it into the directories. When x is negative 1 million, the top doesn't care. The top is just a negative 5. So the top's going to be negative. But when I plug in negative 1 million and add 2, the add 2 is insignificant because the number is so big, it's going to be negative. Which means we'll have a negative on the top and a negative on the bottom, which means it's going to be plus, which is my clue that it is above the horizontal asymptote. Similarly, I'm going to plug in 1 million, positive 1 million. The top is a negative 5. There's no x on the top. It stays, it doesn't care what x is, it stays negative. But the bottom 1 million is positive. So this is going to be a negative divided by a positive, which is negative, which is this signal that this is going to come from below. Which means I now have clues about what this is going to do. From the left, it comes from above, and from the right, it comes from below. Now, our experience is all we could use before, and we kind of knew this was going to happen from experience, but this is the math that proves it's happening. So that's why we're doing it. All right, let's go back and check our thing. We just did the vertical asymptote. We just did the horizontal asymptote. We're now going to do x and y intercepts. I'm just going to do them over here. So the x-intercept is when y equals 0. The y-intercept is when x is 0. And I'll do this quickly because we already did this the other day. So the function is y equals x minus 3 over x plus 2. So I set the y equal to 0. My first step is to bring this up and multiply by 0. Which is good because multiplying by 0 is 0. And solve for x gets me 3 equals x. So there's my x-intercept. The y-intercept happens when x equals 0. So wherever I see an x, I'm going to plug in a 0. So it's 0 minus 3 over 0 plus 2. So y equals negative 3 over 2, which I know is negative 1.5. I might need the decimals so I can picture where it is on the graph. 3 over 2, I kind of know where that is, but negative 1.5 is helpful. So I have my two x and y intercepts. I'll plot those. So the x-intercept was 3, and the y-intercept was negative 1.5. Again, since I'm being more accurate, I am going to label this. Negative 1, negative 2, negative 3, negative 1, negative 2, all those positive. All right. I've got my x and y intercepts. That's great. Let's go back and check my list. I've done that. So next, critical points. So the critical points I'm going to do over here. You can see you need lots of space for this. You'll see on your assignment, I'm giving you a whole page to give you the space. All right, so this function is, this question was x minus 3 over x plus 2. I'm just rewriting it so it's easier to do the derivative. What you should see right now then to do the derivative is I got to use the quotient rule. because I have something on the top and something on the bottom. So derivative of the top times the bottom minus the derivative of the bottom times the top. Let's see if we can get someone who's interested in doing the derivative with me. Anyone?
I can.
Awesome, Jenna. Derivative of the top.
1
Times?
times x plus 2 minus 1 times x minus 3 over x plus 2 squared.
Perfect. Thank you, Jenna. So she did the derivative of the top, which is just 1, times the bottom, minus the derivative of the bottom, which is also just 1, times the top, all over the bottom squared. We can tidy this up a little bit. Rainbow to 1, not very exciting, x plus 2. The second part, we're rainbowing to negative 1, so minus x minus 3, all over the bottom squared. And I'm setting this equal to 0. So although I might be freaking out a little bit because it's the quotient rule and I end up with this big fraction, good news is I'm setting it equal to 0. And so when it's set equal to 0, the thing that's going to happen is that's going to disappear. And I'll be just left with 0 equals. And now on the top, I've got x minus x. That's gone. 2 minus 3 is negative 1. Oh, wait. This should be a plus, shouldn't it? I rainbowed to negative 1. So it's a minus x and then a plus 3. Excuse me. All right, still, x minus x is gone. 2 plus 3 is 5. And I get this statement. This should ring a bunch of alarm bells because I'm pretty confident that 0 is not equal to 5. In fact, that statement is absurd. So just a little throwback to our vector days when we ended up with something that's weird. I said it was absurd. And what this is telling me is I was trying to find all the spots where the derivative was equal to 0. And I end up with this, which means there is no spot that is equal to 0. It's impossible. This is impossible, which means there are no critical points. That's exciting because I don't need to do a chart anymore. I don't need to go any further. I have no more critical points. I have no more information that's going to get me a better graph than what I have right now. And I imagine when I go off and actually graph it now, I'll see the fact that there is no spots where there's any maxes or mins. And we already sketched this yesterday, so this is good news. And so now I know it comes down here, it goes through this point and this point. And I've got this half, and then the rest is going to mimic itself over here, doing something like that. So when I look at the entirety of this question, I see that it is not much different. The graph, we don't get a much more accurate graph than what we got yesterday, but what we do have is a lot more math to prove what we had yesterday is correct. So we did the limit stuff, we used the directrix to find those clues, which we didn't have before. And we proved there's no maxes or mins, and looking at the graph, that makes sense. There's no spots where it's going to get maximum or minimum. And we've got y-intercepts, and so we have our picture. All right, we're doing great. Oh, one last thing I was just going to add on to this. If we were going to do points of inflection and concavity, it would tell us a little bit more about where this goes. Because you kind of just estimate it and eyeball it, okay? So if we were doing that, we're not going to, but if we were, we'd be able to find out a little bit more about this. Where exactly does it curve down? Where is the concavity? Where does it actually happen? Okay, and that one you do the second derivative, set it equals to 0, and it's a whole other chart. But we're not going to go there. We're just going to say we've learned enough. Mr. Lee, stop killing us. We're just going to say, here we go. We're going to get that picture. All right. Really good job. I know it's been a long morning. We have one last example, and this one's going to be the biggest, but it's also going to be where everything comes together. And so it does get kind of exciting. And when you're done sketching this, you're going to be pretty proud of what you've done. All right. So if you haven't started on a new page, start on a new page. Because one page might not be enough for this. Okay. Again, I've chosen to redo a question from our review. This is 3D. So we've done a big chunk of this. We have a pretty good idea, if you wanted to go back and look at it, what the picture is going to look like. But we're going to pretend we haven't done this before. We're going to pretend we're doing this from scratch, and we have no clue what this picture is going to look like. We're going to go through all of our steps: vertical asymptotes, horizontal asymptotes, x and y intercepts, critical points, derivatives, everything like that. All of it will give us clues to get the most accurate sketch of this function as possible. So we start by, of course, looking at it and seeing it is not factored. So what you'll need to do is factor it. Two numbers that multiply to -8 and add to +2. Oh my goodness. So two numbers that multiply to -8 and add to -2 are x plus 4 and x minus 2. You probably saw me cheat there, not because I didn't know what it was. It's just I don't want to make a mistake here, because if I make a mistake here, I am euchred for the rest of this question. So just double check. You could even rainbow it out if you wanted, to know that you'll get a +4, a 2x, because there's a 4 and a -2, yep. And the last number is going to be a -8, yep. All right. So in factored form, we're able to find vertical asymptotes. Let's start with that. Someone tell me the two vertical asymptotes.
-4, 2.
Good. So one of them is -4 and one of them is -2. We're now going to have to test the limit on both of those. The limit as x approaches -4 from the left, and the limit as x approaches -4 from the right. So let's just do -4. Again, we're doing the same thing we did before. In our head, we're going to pick a number just to the left of -4, so like -4.1. But we're not writing it down. We're just going to do it in our head. -4 is obviously going to be negative. -4.1 plus 4 is going to be negative. And then -2 is negative. Negative on the bottom is positive. Negative divided by positive is negative. We got negative infinity. Do +4 again. We're going to do -3.9. You can check the work that we did before to prove this one. -3.9 is going to be positive. and minus, negative of negative is going to be plus. We also have to test the limits on 2. From the left and from the right. Imagining a number like 1.9 and 2.1. 1.9 is minus 4 is going to be that. Plus 4 is going to be positive. Minus 2 is going to get me in the negatives. So that's going to be a positive infinity. And 2.1 minus 4 plus 4 minus 2 is going to be positive this time. 2.1 minus 2 is going to be positive. I'll have positive on the bottom, negative divided by positive is negative, and I get that. So it looks like a little bit more work, but think about what we had to do before with the test points. It's the exact same amount of work. All right, we've got our first clues for our picture. We are going to have an asymptote at -4. And an asymptote at 2. And these limit tests told me that from the left, it's coming down. From the right, it's going up. And on the other one, from the left, it's going up. And from the right, it's coming down. So that should look familiar from what we did yesterday. Next comes our horizontal asymptotes. So I think I'm going to do the horizontal asymptotes over here. The degree in the top. You can look at the original to get that. The degree in the top is 1. Degree in the bottom, you can look from the original and see it's a squared. And so n is less than m. Therefore, y equals 0. Remember, if the big number's on the bottom, then you'll have something like, when these numbers are huge, you'll have something like 1 or 6 over 1 million. And when the number is big on the bottom, that's a really tiny fraction, you get 0. I'm drawing it 0, but I just cheated above so you can see it. Because it's at 0, we don't need a directrix. We can plug in, do the limit test on negative and positive infinity on the original, and it'll be enough. So we don't need the directrix when it's at 0. So let's plug in the limit as x approaches negative infinity on the function, and the limit as x approaches positive infinity on the function. So here you're going to plug in a number like -1 million into the factored form of this. So when you subtract 4, you're going to get that. -1 million plus 4, the plus 4 is insignificant. It's still going to be negative. And obviously -2 is that. So we'll end up with a negative divided by a positive, which is going to be minus, which is telling me it's below. Similarly, when I put in a positive 1 million, the -4 is insignificant. It's still going to be positive. The +4, big deal. -2, big deal. The number is so big that it's going to stay positive. And obviously positive divided by a positive is positive, which means it's going to come from above. And so this little test here tells me that when x is negative infinity, it's coming from below. Not a surprise here because I see that part. But over here, it's coming from above. Maybe a little bit of surprise because I would have guessed that it might be coming down here. But then I remember we have those examples where it has a bump. So I'm going to suggest there's going to be more clues that tell me that this is a bump. That's an awful arrow. Let me get that. All right. Let's go back and check our rules. So we did vertical asymptotes, we did the right and left limits, we did horizontal asymptotes, and we did the negative and positive infinity limits. We didn't need the directrix in this one. So next comes the x and y intercepts. I think I'm going to do the x and y intercepts over here. So the x-intercept is y equals 0. The y-intercept is when x equals 0. So this function, you can choose either the original version of the function or the factored one. I think I'll use the original one. It doesn't really matter much here because it's going to set equal to 0. So x minus 4 over, I'll use this one. It doesn't matter because the first step you're going to multiply by 0. So it doesn't matter what's on the bottom, whether it's factored or not. It's going to be 0. And solving for x is going to get x equals 4. Just as a heads up, there might be some that don't have x-intercepts, which when you go off and do this step, you'll get something absurd. You'll get something like 0 equals 4, which of course means there's no x-intercepts. This one does, it's right there. The y-intercept is when x equals 0. So I'm going to plug in this. So 0 minus 4 on the top, 0 squared plus 2 times 0 minus 8 on the bottom. So that's negative 4 on the top and negative 8 on the bottom. Y equals 1/2. So 2 more clues for our picture. And again, I think we already knew this from before. So x equals 4. So there it is, good. I was hoping there'd be a spot where it would cross because my other clue told me it was coming from above. And my y-intercept was 1/2. So it comes down there. Good, another bit of information to get my picture even more accurate. So far, everything feels the same, except for using limits instead of the test points. But this is where we would have stopped and drawn a picture. But now, with the critical points, we can go off and get more information. So, next, we're going to do the first derivative test to look for critical points. So, the original question is x minus 4 over x squared plus 2x minus 8. I'm not going to use the factored form to differentiate, because if I differentiate the factored form, you'd have like a product rule on the bottom, and I know how to differentiate this quadratic, so I think I'm going to use the original. Okay, so just as a little heads up. Let's do the derivative. And I think you guys are good enough to do this here. The derivative of the top is 1 times the bottom minus the derivative of the bottom. So the derivative of the bottom is 2x plus 2. Just running out of room here, so I'm just going to move it down. So that's the derivative of the bottom times the top, x minus 4, all over the bottom squared. And I don't care how nasty the bottom squared is, because in a moment I'm going to set it equal to 0. I'll clean this up. Rainbow to 1, not very exciting. Here, I get a rainbow the second one, and this is subtract. So I'm going to do this in 2 steps. You might be able to do it in 1 step. I'm going to rainbow first, and then, or do rainbow here, then I'll rainbow the -1. So 2x times x is 2x squared minus 8x plus 2x minus 8. All over the bottom squared. But the bottom is going to come up and multiply by 0. So good news is that's going to disappear. And I will get 0 equals x squared plus 2x minus 8. Now I'm going to rainbow the negative. So it's minus 2x squared plus 8x minus 2x plus 8. Oh, I don't need that anymore because it's gone. Minus 2x plus 8. Let's collect like terms. X squared minus 2x is minus x squared. And then I've got a 2x and a minus 2x, so that's going to be gone. And that means I'm going to be just left with 8x. And then a minus 8 and a plus 8 disappeared. That's not always going to happen, but it did in this one. You might end up with a number, and then you'll have a quadratic that you'll factor, just like in that little heads up that we had before. And here is that little warning that I warned you about before, in that we have a negative out front. Normally we divide both sides by negative and get rid of it, but we need to keep it because that negative really significantly tells us whether it opens down or up or anything like that. So we're going to keep it and factor this. This is not a complete trinomial, so the easiest way to factor is common factor. And so I'm going to take out the negative x, keeping that negative there. Dividing out a negative x is going to leave that with an x minus an 8. Again, you can always check to see if you did that right by going backwards. Negative x times x is negative x squared, good. Negative x times negative 8 is positive 8x, good. And so I do all this so that I can get the zeros. So obviously one of the answers is 0. And I think you can see the other answer is 8. And so I have 2 critical points. I would not have known about these critical points without the calculus. Okay? And so this is really handy. Not only do I know the x values, but I have to figure out the actual coordinates. So I have to take this and plug it into the original. F at 0, and then F at 8. So plugging it up into the very top, I think I'm going to plug it into the factored form. Just makes my math a little bit easier, although it doesn't matter which one I plug it into. But I'm going to plug it into the factored form. So x minus 4 over, and again, if you want to see this factored form, it's up at the top. It's on your page. X plus 2, x minus 2, or x plus 4, x minus 2. So x plus 4 is 0 plus 4, and x minus 2 is 0 minus 2. You can see how this math is a little bit easier. So that's negative 4 on the top. And 4 times negative 2 is negative 8. So that's going to reduce to 1/2. And therefore, I've got a point at 0, 1/2. That is a critical point. Over here, give myself a little more room. F at 8, so it's 8 minus 4 over 8 plus 4, and 8 minus 2. 8 minus 4 is 4. 8 plus 2 is 12. And 8 minus 2 is 6. So I get 4 over 72, which is a great point. 8, 4 over 72. But if I have to graph that, I think I probably want the decimal. And the decimal is 0.0556, like that. I know that that's going to be really hard for me to graph 0.05. So I'll have to deal with that in a second. Let's deal with it right now. I don't know if this is going to work well. Go ahead. Yeah, that's not going to be. All right. So I've got two critical points. Just looking at my notes. One of them is 0 and 1/2. Well, guess what? I already knew that y-intercept. So it turns out that that's a critical point. That's not always going to happen. The critical point might be someplace else, and the y-intercept might be someplace else. This one happened to be there. The other one was at 8 and 0.056. So the key is I now know where that bump is. I didn't know where the bump was before, but now I know it's right here. Now, that's an awful spot. It should be way closer to the thing, but I'm going to exaggerate that spot, okay? And I can help the reader by telling them where that spot is. That spot is 8 and 4/72. Okay, that fraction's better than the decimal, but it's telling you where that spot is. Okay? All right, I should also plot this other point is 0 and 1/2. Now, this is great, but I haven't proven whether they are maximums and minimums. Even though I'm pretty confident that this bump is going to be a local max, and this part here is going to be the bottom of some shape, I need to do the proof. So my last step in all of this, thank goodness, is to do my chart. So I think I've got a little opening here where I'm going to do my chart. So remember, we're looking at the intervals. What does the derivative do? And therefore, what does the original do? Remember that my critical points, if I imagine the number line, one of the critical points is 0, one of them is 8. I want to know before, I want to know middle, and I want to know after. Is anyone interested in telling me the intervals that I write on the top of my chart? All right.
I can try.
Okay, Delaney, great.
So it's when x is smaller than 0.
Perfect, good.
And then when x is 0.
Yep.
And then when x is greater than 0 but smaller than 8.
Right.
And then when x is 8.
Mm-hmm.
And then when x is greater than 8.
Perfect. Good job. Okay. And this little number line I draw is meant to help you with these points, especially that middle section, right? X or 0 is less than x and less than 8. Like it's right there in the number line. And then this is x is less than 0, and this is x is greater than 8. Okay? So if you draw that little number line, it will help you with this stuff here. All right. I'm doing this chart by testing the derivative. I'm definitely not going to use this version of the derivative up here. Definitely not going to use that. I could use this version right here, but it's not in factored form. So I'm going to use this version right here to do my testing. And again, this is where that negative comes in. It's going to have a big influence on my graph. So don't forget about that negative. All right. So we need to then choose numbers in the interval and test it on the derivative. First number is something less than 0. I'm going to choose -1. If I put -1 in here, it's negative negative. So putting a -1 in there actually turns it positive. -1 minus 8 is going to be negative, which means I'll have a positive times a negative, which is going to be negative. So this graph is going to go down at the first part. Zero, I know it's 0. 8, I know it's 0. Choose a number now between 0 and 8. Again, let's choose something easy. I'm going to choose 1. If I put in 1, it becomes negative because of the negative symbol. 1 minus 8 is going to be negative. And so this is going to be a negative times a negative, which is positive. So this is going up. And lastly, I'm going to choose a bigger number than 8, something like 9 or 10. If I put in 10, it becomes negative right away. And 10 minus 8 is going to be positive. Anything bigger than 8 is going to be positive. And so it's a negative times a positive, which is negative, which means this is going to go down. And here then is our proof that it goes down and then up. So down and then up means that we're at a local minimum. And then this is going up and then down, and this is our bump, isn't it? So it is a local max. So there's all the proof to demonstrate that my spots, my points, are maxes and mins. So this indeed is a minimum, and this indeed is a maximum. Local maximum, right? You already see points up here that are going to be bigger than this guy, and you already see points down here that are going to be lower than this guy. But locally, it's the big cheese. And now I finish off my sketching just like I finished before, except with a little more accuracy. So this graph is going to come down here, and then it's going to go over to this lowest point, and then come back up. Don't accidentally draw one lower than that spot. That's the lowest point. I don't even know if I'm happy with that. I'm going to really make sure that nobody questions that this is the lowest point. So I'm going to come down like this and then really emphasize that that's the lowest point. Okay? Now I feel really good that that's the lowest point. Over here, I'm going to have it come up, and it only comes up a little bit, but I'm going to have to exaggerate that on my picture. So I'm going to have it come up like this, and then try and make this the highest point, and then come back down. Okay? I know that it's a challenge to actually draw that without accidentally going higher than that spot and then somehow coming down, but we're going to have that as a really good attempt. And then over here, don't forget about this part, which we don't have any other clues about. And there is our picture. And this is where we take a step back. We look at this entire answer and be amazed at what we're doing, okay? You can give yourself a little round of applause. Let's look at all the stuff we're doing here. You can see why we saved this to the end of the year, because it really puts all sorts of stuff together. Uses our calculus, uses our stuff from advanced functions, allows us to get the most accurate representation possible, okay? And you can see, like, this is almost more than a page worth of work. When I do these on a page, I really try and write small but neat, not too small that I can't read it, so that I can get everything in. Right? I can usually do it all on one page. The Smartboard page isn't quite as friendly. Just as my last little proof, I'm going to show you that these numbers are correct from Desmos. And look at our picture. You can see that that definitely looks like our picture. You don't have the asymptotes there because they're not drawn, but you can see where they would exist. I'll make this a little fatter so you can see it. Maybe make it green. Okay, so you can see that. And you can also see Desmos wants to tell me some important spots. You can see them there as gray. And so I can go over here and click on this and see that the lowest point is 0 and 0.5, which is what we proved. We can also see the x-intercept at 4 and 0. And then it's even telling me, it wants to tell me about that other critical point way out here. And look at that. It says it's 8 and 0.0556 or whatever, it rounds it to that. And that is exactly the point that we figured out all the way down here. There it is. Okay? So, really, really good job with all of this. Hopefully you're understanding. We know we were a little quiet, but we've had a good run with this. So, because these questions are so big, you're going to be just doing an assignment on this. I have given you, I'll give it to you now. So I have given you the option of printing out this assignment. It's just a blank page with the question and a grid on it. You're welcome to use this, but you don't have to. Some of you might be more comfortable in just doing it on a piece of graph paper and making your own grid. Totally fine, okay? If you can, try and make it on at least one full page so that everything's on one page so I can see it at once. But if you find it's too much and you need to go on to a second page, that's fine. I'm not going to be upset about that. I've had people do all the math on one page and then just go and do a grid on its own on a piece of graph paper. If you want to do that, that's fine. Okay, but this is at your disposal. There are 4 of these. Okay, so the first one's a polynomial. The second is a basic rational function. And then the last 2 are like the ones we just did. Here's one similar to one we just did. And here's another one that's already been factored for you. Okay? So there are 4 there. Each of them is worth 10 marks because there's so many things that you're going to be going at. And the whole thing is worth 40. I put the due date on Monday, but not any specific time on Monday, because I want you to tell me what you need to do between the next couple of days. But we are going to dismiss ourselves here for lunch, and we don't need to come back. So you have the entire afternoon to work on these. You have the weekend if you'd like. And then even if you know you have a crazy time and you need some time on Monday, you can. We are going to be doing new stuff on Monday, but Monday will be our last day of lessons. And then this assignment will be due sometime on Monday. The sooner you do it, the sooner you hand it in, the easier it is for me. But just wanted to give you as much time to do all the sketching because I know these do take a little bit of time. That last one, we just took half an hour to do that one last question. Okay? It's going to be the longest. You've got 2 about that are like that. The other 2 are shorter. All right? Are there any questions before I say goodbye? Okay, if you could just turn your cameras on. All right. So let's see, thumbs up, how we're doing with this stuff. A little overwhelming. Oh, good. Good. Okay, cool. I'm seeing some pretty good stuff there. All right, good. I recognize it's a lot, but do recognize the end is in sight. And so make sure we take advantage of that. Also, you know, like I've given you the time this afternoon because I want you to also give yourself some time This is not going to take you the whole weekend to do. You will have some time on Monday. So do take advantage of the nice weather, get outside and do all that sort of stuff too. Okay. You guys have been doing an exceptional job. I'm really proud of how things are going. So keep up the work for the last little bit of this course, and then we'll be able to catch our breath. Okay, any questions before I say goodbye? Okay, one last thing. I'm just going to release the Friday check-in. This will be the last one that you do, well, the last Friday check-in you'll do. It'll come out in a couple of minutes. So if you wouldn't mind sometime between now and the end of the weekend, if you wouldn't spend a couple of minutes and just give me a check-in, just want to always see how you're doing before we wrap up the course. Okay? All right. So thanks very much. And Mia, thank you for waving as always. The rest of you, maybe you could get, oh, there we go. All right, good. Have a great weekend. Take care, everybody. Bye.